Hello everyone. In this lecture, we are gonna solve more examples of calculating hydrostatic forces on different planes and objects. So first, I'm going to solve one example of an inclined plane, and then a vertical plane, and after that, we are gonna solve some examples for calculating hydrostatic pressure force on a curved surface. Okay, so these three type of problems. So in this example, I want to find and calculate the hydrostatic force exerted on a shaft. It's kind of an inclined plane. So the question that we have asks us to determine the magnitude and location of the resultant force on the gate by the water. And B, the moment that would have to be applied to the shaft to open the gate. Okay, so first we want to determine the magnitude and location of the resultant force on the gate by the water, and then we want to calculate the moment that would have to be applied to the shaft to open the gate. So this is the geometry of our problem. So we have a shaft here which is located at this location. Okay, and we have some water on top of that, which is located at this surface. Okay. And the depth of the water to the center of the shaft is 8 meters as given in this problem here. Okay. And so this is the side view of the shaft in here. Here we have a side view. Okay. This is the top view. If you look at it from top, this is a shaft. So this is a circle. It's like a circle shaft, and then here is again the side view. We have the side view, which is free body diagram of the forces. Okay, so now given this and given the calculations we had for the side inclined plane here, I want to calculate the magnitude and also the location of the resultant force. Okay. Okay, let me see. Think. Okay. So let's first find the magnitude of this force. So answer. So the magnitude is not that difficult, okay? The magnitude, as we know from the previous work is this is gonna be rho g y c sine theta times a, or rho g h c times a, where h is the height of the center, and then we have to multiply that by the area of the shaft. Okay, so to get the resultant force, the magnitude of the resultant force. So it's gonna be Fr equals to rho g hc times a. So it's gonna be, the rho of water is 10 to the 3, and then g is 9.81, and hc is given in the problem, so it's the distance from the center of the shaft to the free surface of the water. So it's gonna be 8 meter, right? It's given here, and this is the center of that, the centroid. So we just write 8, and then we have the area of this shaft. So the area of this shaft, I think, yeah. So here we have this, the diameter of that is 4 meter, right? So the diameter of this shaft is given, which is 4 meter. So the radius of the shaft, which is from here to here, should be 2 meters, right? So the area of that should be pi times r squared, which is going to be times 2 to the power 2. Okay? And if you calculate this, this is going to give us 985.7 kilonewton. Okay? So calculating the magnitude is pretty easy. Okay. Finding the location is a little bit more complicated, because for the magnitude we just needed to calculate the first moment of the area, and for the location we need to calculate the second moment of area. Okay, so let's go to the location. So to find the location, we use this formula here for the YR, the resultant, the location of the resultant force is going to be YR equals to IXC over YCA plus Y of the centroid. Okay. So the I over this x, if this is x, we have to get the I over this, the moment of inertia around this axis, and then divided by yc times a plus yc. Okay, so this is going to be the yr, the location of y from the y, right? If this is I, and this is going to be yr, right? This is the location where it is going to be, and this is the centroid of that. Okay, which is going to be, this is going to be yc, right? From here to here we have yc. Okay, and then xr is gonna be I x yc over yca plus xc. Okay, so to find the fr, what is going to be the x of that? So we have to calculate this formula, which is the moment of inertia of axy of the centroid over yc a plus xc, and because ixyc for circle is 0, because it's symmetrical because of symmetry. So, and we have it here, right? ixyc of a circle is 0. So xr is gonna be xc. So this means, and this is something you'd expect, right, from this graph and from this diagram. You would expect, because of symmetry, Fr, the resultant force, should be and this here, right? In this, if this is x, it should be around this, right? It should not be like here or here, right? So xr and xc should be the same, right? So the x of c, if for example, x of c, whatever it is, say if your coordinate system is from here, so this is gonna be your yc, so let me draw it again. So this is gonna be your yc, and this is gonna be your xc, right? So we expect the fr should be on this line, somewhere in this line, and so its x, the xr, should also be equal to xc, right? But yr can be different. Yr could be, it should be a little bit further down the centroid. Okay, so this is going to be yr. Okay, so this is what we also expected from this figure, and we can also get it from these equations that we introduced. Okay, so now let's calculate yr. So what is going to be the location of resultant force? So yr, so let me first calculate ixc. So ixc for a circle, right? What is that gonna be? So for a circle, we have the formula here. So it's gonna be pi r4 over 4. So I just wanna write it down. Let me write it here. Ixc is gonna be pi r4 over 4. And what is yc? We have to find it from trigonometric relations. So yc, we don't have yc, we have to find yc. Yc is going to be from here to here, right? We don't know that. So we can find it from the given information in this problem. How? It's easy. So you have this triangle. I just draw it again. We have this triangle here with 60 degrees. Okay. And then we know this side of that, which is 8 meter, and we don't know this. So let's see, this is yc, okay? Because up to here is 8 meter based on what is given in the problem, right? This is 8 meter. So what is yc? So as you see here, the sine of 60 is gonna be 8 over yc. So yc is gonna be 8 times sine of 60, right? Let me make sure I am right. Yes, so it's going to be 8 over yc, and so yc is going to be, I made a mistake here, so yc should be 8 over sine 60, right? Because you just need to put it here, because yc times sine 60 is gonna be 8, right? So yc is gonna be 8 over sine 60. So I want to have this relation and just put it there into, substitute into my equations. So yc is gonna be 8 over sine 60. So let me write it down. Yc is gonna be 8 meter over sine 60. Okay, so Ixc, we have that, and now I want to substitute that into yr and get the value of yr. So yr is gonna be pi Ixc, which is gonna be pi over 4 times r to the power 4, which is 2 to power 4 of meter also to power 4 over yc, which is going to be 8 meter over sine 60 times a is pr squared, right? So we are going to have pi times 2 to power 2 and meter square. Okay, so these two are going to cancel out, so we are going to have 2 to power 2, and then these three also going to cancel out. We are going to have meter here, so this is correct. This is going to be a length, and then we have this plus yc, which is, what is yc? It is 8 meter over sine 60. Okay, so let's see what we have. We are going to have, and then these two also are going to cancel out, 2 to power 2 and 4. So we are going to have sine 60, and these two also going to cancel out, this pi. We're going to have sine 60 over 8 plus 8 over sine 60, which is going to be, if you calculate, it's going to be 0.108 plus 926, which is going to be 9.37 meter. Okay, so the location of this resultant force, or yr, which is going to be somewhere around here if I want to show it, is going to be around 9.37 meter from the origin. Okay, this is the location of that, and the magnitude of that is going to be 985.7 kilonewton. Okay, so this is how we can get these numbers and find the location and the magnitude of that force. Okay, so now we want to solve the second part of the question, which seeks the moment that would have to be applied to the shaft to open the gate. Okay, so what is the moment that has to be applied to this gate to open it? Okay, we can calculate it from here. So how much we have to calculate this moment around this shape. So I'm gonna do it. So B, the moment to open the gate. So I'm gonna write that the moment around the center of this gate to be 0. Okay, and then I want to calculate the moment around the center of this gate. Okay, so I have it here. Let me calculate it here, and then we will add it to, we will write it later. So what is the sigma of MC, the moment around the center? So we have FR, which is going to give us this moment around here, right? So we have FR times, the moment is going to be FR times YR minus YC, right? This is going to be the moment around the center. And why I do calculate it around the center? The reason is we also have the weight, okay? So if you were to calculate it, for example, around point O, the origin, if you want to calculate moment around origin, then you would have FR times YR, which is going to give us this moment, but you also have the weight. So the weight of that is going to also give us another moment, right? So it's going to give us also another moment. And then you need to know the weight of this shaft, but this is not given in this problem, right? So in order to avoid that, we can simply calculate the moment around the center, okay? So to find, and we know that this should be, the sum of that should be 0 if we want, if we want it to not to open, okay? So this is how much moment this has to be able to tolerate. Otherwise, if it doesn't tolerate this moment around the center, for example, this moment can be given to this from any of the joints here, right? If it has, it is kind of connected, any connections like from the sides, it can, this moment can be given to that in order for it to keep it closed, okay? Otherwise, the moment that is given to this shaft is calculated as I showed you. So it's going to be, if you write it around center, the moment around the center is going to be FR times this length here, which is YR minus YC, right? So this is YC. Okay, so we are going to have FR times YR minus YC. This is going to be the moment, and the weight is not going to count because the location of it is right at the center, so the length to that force is just 0. Okay, so we have eliminated the weight here. Okay, so let me now write this down. It's not that difficult. So we are going to get M is going to be the moment is gonna be Fr times YR minus YC, which is gonna be what? Which is gonna be Fr is 958.7 kilonewton. So we have it 958.7 times 10 to the power 3 Newton times YR minus YC, which is going to be 9.37 minus YC, which is 8 over sine 60, or this one. Okay, so it's going to be simply this value, which is 0.108 meter. And this is going to give us 104 times 10 to the power 5 Newton meter. So this is going to be the amount of moment that is needed to keep the gate closed, or how much moment it is given to this shaft by the water, right? How much moment is applied to this shaft by the water above that. Okay, so this was one example for an inclined plane. So simply we need to, in order to solve these we need to use these relations that we derived here. So the magnitude is easy. You just look at the centroid of the object, and then you find h of that, the height of that, and then you multiply it by rho g and a. You will get the resultant force, and for the location you would need to use this formula here for the second area of moment or inertia. Okay, so now let me solve another example for calculating the force on a vertical plane. So let me write it down here. Determine the magnitude and location of the force of the seawater on the illustrated triangular area. And the gamma of water, which is a specific weight, or rho g of the water, rho water g, is given as 64 pound per foot cube. Okay, so now we are in the British system. Okay, so the question wants us, in this tank of water, we have a water here. This is a tank of water. Okay, this is all water here. So the question wants us to find the magnitude and location of the force of this seawater on this triangular area here. Okay, so let me show this with this color. So this is a vertical plane, right? This is not inclined. The water is just exerting a force. So this is like something like this. Okay, we have pressure here. So this is a vertical plane. And now we want to find what is the magnitude of the force and also the location of the force on this inclined, not inclined, on this vertical plane, okay? So we have a vertical plane. So for a vertical plane, we had this formula here, okay? So for the magnitude and the location, so we can still use the same formula. So the resultant force is gonna be rho GH or gamma HC, so gamma HCA, okay? And so we need to find what are these, okay? HC for a triangle, okay? So if we had, say, if we had a rectangle here instead of a triangle, what would the HC be? The HC would be the center, right? For a rectangle, right? So HC would be 0.15 from the 0.15 foot from the bottom of that. And then we have 2 foot, so we had to just minus 2 minus 15. Okay, but how about a how about a triangle? Okay, so let me calculate it. So it's pretty easy. Again, you can look at the tables, but for a triangle, these are the relations for first and second moment. So we have a triangle like this. And then we have water on top of that. So the centroid of that is going to be somewhere around here, right? So this is I'm gonna write it as YC, which is the centroid of this. Okay. And the second area of moment, it is going to be around somewhere CP, which I'm going to show it here. So it will have an XR from here, the resultant, and also a YR from here. So the first area of moment and second area of moment. Okay. So for a rectangle, for a triangle, if we have a triangle like this with 2 different sides of A and B, let me try it again. These are the second area of moments for this for a triangle. These are given from say from a table. So it's going to be BA cubed over 36, and IXYC is going to be BA square over 72 times B. So these we can find from a table. Okay, this will be given in a even in homework or in test, or you can in homework you can use the table from the book, or for in the test it will be given to you. Okay, so this CP is the center of pressure. Okay, for the second area of moment. So now let's find first the magnitude of this force, and then we are gonna solve find the location of that. So the magnitude, as I said, is gonna be gamma of water, right? This is water, so it's gonna be gamma water times HC times A. So what is HC? HC is gonna be the centroid. Also, these are given in the tables. This is going to be 1/3 of that side, so it's going to be 0.1 foot, and then this is going to be 2/3 of that, so this is going to be 0.2 foot. Okay, and the whole thing is given in the problem, so the whole thing I forgot to remove that side because we don't have any rectangle here. Okay, I guess I have to do that again. So now I wanted to mention that this is for a triangle, and the one side of this is given to us, right? So one side of it is 2 foot, which is given. Okay. So from here to here, we know that is gonna be 2 foot. Let me maybe show it with this. Yeah. So from here to here is given in the problem configuration, which is from here to here is 2 foot, right? And you can see it from here. Right, 2 foot. Okay. So we have gamma water HCA. So what is going to be HC? HC is going to be from here to here, right? HC or YC are here the same. So it's going to be, what is gamma water? Gamma water is given in the problem is 64. So I just write it down, 64 pounds per foot cube times HC. HC is going to be 2 foot minus 0.1 foot, right? So it's going to be 1.9 foot. Times A. What is A? A is going to be the area of that. So it's going to be 1/2 of 0.3 foot square, right? And this is gonna give me 5.47 pound. So this is going to be the magnitude of the force that is applied to this triangular area, okay, by the water. So just something I want you to make sure and double check is the units, okay? Especially in exams, I see some people get confused with these units, and then they kind of, for example, this is a common mistake that I've seen. They multiply gamma by g, which you shouldn't do that, right? Because gamma already has g in it. So if you write the units, and then you also look at the final units, so these foods are gonna all cancel out, and you are only left with pound, which is the unit for force. Then this means you have done you have done all the process and multiplications correctly. Okay, so make sure you double check the units whenever you kind of solve these problems. Okay, so now we want to solve and find the center of the pressure, or the location of this force, which I have shown, the resultant force, which I have shown with this YR and XR here, right? So this is going to be where this force is going to be applied. So it's kind of somewhere around here. This is the resultant force. This is going to be applied somewhere around here. So if I show it in 3D format, so it's going to be somewhere around here, right? From the back. Not, yeah. You have to maybe zoom so you can better understand what I mean. So it's going to be something like this, right? From the back of it. Okay. So this is going to be the location of this force. And now I'm interested to find that location. Okay, so the center of pressure is gonna be YR equals to IXC over YCA plus YC from the formula that we had before, right? So I just substitute all the things here, right? I have IXC, so this is the IXC of that, okay, the moment around here. So X is here, this is X. Let me show it again. This is X, and this is Y direction, okay, the coordinate system. IXC means from here, right? This is going to be X. This is going to be Y, XC and YC. So the moment of XC is going to be around this. So let me just write it. I have it here. It's going to be BA cubed over 36. And B and A are equal here to 0.3. So I just write it down. So it equals to 0.3 foot times 0.3 foot cube over 36 plus YC is 1.9 foot, found it from here, and this is gonna be if you calculate it, this is gonna be 0.0026 foot plus I forgot to multiply this by this is IXC by YC times A, so YC is 1.9 foot, and then we also have A, which is going to be the area of that, which is here. So let me rewrite it again. So 36. So we have over 36 times YC, where YC is 1.9 foot. And then we have A is going to be 0.3 square foot square over 2. Okay. So all these foots are gonna cancel out, and you will only have foot here. These two are gonna also cancel out. So this means this is correct. This should be has the unit of length, which is foot. So the whole thing here is gonna be, if you calculate it in a calculator, it's gonna be 0.0026 foot. And then we have plus 1.9 foot, which is gonna give us 1.90026 foot. Okay. It's very close to the center. To the center or area of the center of pressure is very close to the center of area here. It's only the difference is only in this, which is pretty small, but it still is not exactly there, and we need to know that for specially designed problems that this is not exactly there. And similarly for XR, we have, so XR is gonna be IXYC over YCA plus XC. Okay, so IXC is given here, IXYC is given BA squared over 72 times B. So it's gonna be 0.3 foot times 0.3 foot square over 72 Let me first calculate IXYC, and then we are going to calculate that. So IXYC is going to be 0.3 foot square, 0.3 foot times 0.3 foot square over 72 times 0.3 foot. This equals to 0.0081 foot to power 4 over 72. And then I want to calculate XR. So XR is going to be 0.0081 foot to power 4 over 72 times 1.9 foot, which is YC, times A is going to be 0.3 square foot square over 2, just from here. Plus XC. What is XC? XC is here. This is XC, which is going to be, again, because this is all symmetrical, it's going to be 0.1 foot. So I will just write it down. So it's going to be plus 1 foot, which equals to 0.10113 foot. Okay, so this is going to be the center of this force here, the center of pressure, which we call the center of pressure. Okay, so this is how you should kind of solve these problems. So with the formulas that were given, we are going to solve these problems, and then in the next sessions, after the break, I'm gonna solve some more examples of these pressure and calculating hydrostatic forces on different planes and objects. I'm gonna introduce pressure prism concept and also calculate hydrostatic pressure force on a curved surface, okay? So let me just briefly review what we learned today. So I've solved two examples. One for calculating the forces on an inclined plane on a shaft here, as you see it. Okay, so for the resultant force, we simply calculate this rho g HCA, where HC is the center of the area of that plane. Okay. And so it's easy for the magnitude of the force, and for the location of the resultant force, we use this formula for y, and simply for x also we use xr is ixyc plus yc over yca plus xc, and because for the circle ixyc is 0 because of symmetry, so xr equals to xc. And these are also the things that we used from the table. IXC, we have it from the tables. And YC is given from, we calculated based on trigonometric relations in these examples. So this gives us also the location of the resultant force. And for the moment, we just simply calculate the moment around the center of this shaft to kind of avoid the weight of that. So it's going to be FR times YR minus YC, which is going to give us this magnitude. And then the second question was about calculating the location of the magnitude and the location of the force on this triangular shape here. Okay, so the magnitude is easy. It's going to be gamma HCA, which we calculated. And the location of it is going to be, we're going to calculate the center of the pressure using these formulas again. So YR, we calculated it, and for XR, because this is a triangle, it's not going to be 0, so it's going to be AXYC plus XC over YCA, and these are given in the problem. So simply we just plug those numbers in, and we are going to get the location of the resultant force as well.